This is our first class of the chapter Applications of Derivatives, and also the last chapter going by your first book. So this is the first topic that which we are going to cover up. Now before we start off, let us see how many different topics we have. We have derivatives as a rate measure, tangent and normal, approximation, increasing and decreasing functions, and maxima and minima. And this is quite a big chapter because all these topics are pretty much theoretical and require some understanding. So we will be starting off with our first topic today, that is derivatives as rate measure. So let us start off with the idea. So what it is, now this is a little bit more physics based, so which you have already done in your previously in physics, so won't be a big problem. So now we already know that rate of change of any quantity, any physical quantity, with respect to another quantity is represented by derivative. So if I want rate of change of y with respect to x, then I denote it by dy by dx at any instant, obviously at any given instant. So for example, if we are talking about velocity, so velocity is something which we already know. It is the rate of change of distance or rate of change of position with respect to time. So if r represents the position of an object at a particular instant and t is the time and v is representing the velocity, then obviously we know that v is dr by dt, and obviously it is represent the unit. Now obviously, as we are talking about physical quantity, the units are very important and we must not forget to put the units here. So how the units work? Well, obviously it is when we are doing the derivative, as I am writing dr by dt, it means the unit of r divided by unit of t. So for here, unit of r, that is meter, and unit of t, that is time, which is second. So therefore our unit is going to be meter per second. Now obviously there can be interconversions in the unit from meter to kilometers or seconds to hours. So those conversions are understood, which if required in a problem, you can do the conversion. Then again, if I talk about, say, area. So area of an object, if I'm denoting it by capital A and it is changing with respect to time, then definitely the rate of change of area with respect to time will be denoted by d capital A by dt, and obviously again the unit will be meter square per second. Meter square is the unit of area and second is the unit of time, and so therefore the unit of the rate of change will be given by meter square per second. Then again, if I am talking about volume of a sphere, and let me denote it by capital V, and I am looking for the rate of change of volume with respect to the radius. Now small r is representing the radius, so therefore the rate of change of volume with respect to the radius will be given by dv by dr, and in this case the unit is going to be, as I mentioned, unit of volume by unit of radius, that is meter cube per meter. Now obviously you will be tempted to write it as meter square, but do not write it. Why? Because meter cube per meter is denoting the rate of change of volume with respect to the radius, but if I write meter square, that means I am denoting an area. So meters cube per meter and meter square are not two same thing. So do understand this unit, the idea of unit is not exactly same as how it works for the physical quantity, because when we are representing any physical quantity by its unit, it has to be different for two things. So obviously if the rate of change of volume with respect to the radius, if that becomes equal to the area, equal to the unit of area, then the idea doesn't stand quite well. So therefore we have to do some differentiation in the sense we have to differentiate the ideas separately. So area and rate of change of volume with respect to radius, they are not two same things. So therefore we are going to write meter cube per meter instead, but not meter square. So keeping all these ideas in mind, so let us start off with some problem. So let us take the first problem, or before we take the first problem, let us go into some of the known figures in a 2D and 3D figures, and let's just recap their areas and perimeter formulas. Why? Because we may be requiring them to solve our problems. And let us start off with square. Obviously we know its area is a square and its perimeter is 4a. Then if we go into rectangle, then it is length into breadth, that is the area, and perimeter is twice of length plus breadth. Then if I go into a rhombus, now rhombus is half times the product of their diagonals, obviously if it is given. And again perimeter is same as for a, where a is the side of the rhombus. Then again for a parallelogram, the area is base into height, obviously base and height to be given, and its perimeter is same as that of rectangle, that is twice of length plus breadth. Then circle, obviously it is pi r squared, that is the area, and 2 pi r is the circumference. And for a triangle, now for a triangle obviously there are different kinds of triangle, but in most of the cases, the general cases, the area is given by half into base into height if the base and the height is known, or we can use the Heron's formula, which is the more general version of the formula, that is under root s into s minus a into s minus b into s minus c, where s is the semi perimeter and small a, small b, small c are the sides of the triangle. And in any case the perimeter will be a plus b plus c. Fine, that is the sum of the three sides. Now let us move to 3D objects. Now in case of 3D objects, we have volumes and surface areas. So let us start off with cube. In case of cube, the volume is a cube, a being the edge of the cube, and obviously the surface area. Now obviously there are two kinds of surface area: TSA, that is the total surface area, and LSA, that is the lateral surface area. Now TSA means it is the sum of all the areas of all the surface. So a cube has got 6 different surfaces, and each and every surface has got an area of a square. So therefore the total surface area will be 6a square. And in case of lateral surface, now lateral surface means area of the 4 walls. Now in case of area of the 4 walls, obviously there are 4 binding walls for any cube. So therefore the lateral surface area will be 4a square. Let us come to cuboid. Now cuboid volume is length into breadth into height, and its total surface area will be twice of length into breadth plus breadth into height plus height into length. Now these are all your childhood memories, just ensure you recap. And lateral surface area will be twice of L plus B into H. Then let us come to cylinder. Now for cylinder, the volume is pi r square h, r being the radius of the base and h being the height of the cylinder. And total surface area is going to be 2 pi r into r plus h. And CSA means the curved surface area, which is pretty much the lateral surface area, but in case of cylinder we are going to term it as the curved surface area, and we are getting the curved surface area as 2 pi r into h. Then we have a cone. For a cone, the volume is 1/3 pi r square h. So we know if I have same radius and same height for a cone and a cylinder, then the volume of a cone is exactly 1/3 of that of the cylinder. Now the total surface area is pi r into r plus L, and curved surface area is pi r L, where L is the slant height. What is the slant height? It is the length along the surface of the cone. If you measure the length along the surface of the cone, then that length is called the slant height of the cone. Then I have a sphere. For a sphere, its volume is 4/3 pi r cube, and its surface area is 4 pi r square. Now obviously a sphere is a single surface, so therefore it doesn't have any separate total surface area or a curved surface area, it has got only one surface area, and that is 4 pi r square. Then I have a hemisphere. Now obviously I am talking about a solid hemisphere, and in that case a solid hemisphere has got a volume 2 pi r cube, 2 by 3 pi r cube. Now doesn't matter if it is solid or hollow, but hemisphere is always going to have the same volume. Now the total surface area and curved surface area, now this is something that matters. In case of a hollow cylinder, we don't have a total surface area, it will only have a curved surface area, and that is 2 pi r square. That is half of the surface area of the sphere. But in case of a solid hemisphere, we also have a total surface area, that is the curved surface area plus the area of its base, that is together 3 pi r square. Fine. So we need not just break our head on how it is coming, and if you don't remember how it is coming, don't bother at all. Just go on with the formulas, because at this time you really need not understand how it comes, you just need to remember these formulas. So now once we have understood, or once we have remembered all these formulas, so let us just start off with our problem. So let us take the first one. So the question asking, find the rate of change of area of a circle with respect to its radius when the radius is 6 centimeter. So let us understand what is given. So I am asked to find out the rate of change of area of a circle, right, with respect to the radius when the radius is 6 centimeters. So let us start off. So what is the area of a circle first? It is pi r square. So now the rate of change of its area with respect to the radius is given by dA dr, and that is exactly 2 pi r. Now obviously r, the value of r is given here as 6. So put the value of r, and now we have 12 pi. So therefore the rate of change of area with respect to radius is 12 pi centimeter square per centimeter. So always remember that the unit is very important, and please ensure you write the unit properly. So it is rate of change of area with respect to radius. So unit of area is centimeter square, unit of radius is centimeter. So therefore it is centimeter square per centimeter, right? And please ensure you write the final statement. Then problem number 2, the radius of a soap bubble is increasing at the rate of half centimeter per second. At what rate the volume is increasing when the radius is 1 centimeter? Now obviously here half centimeter per second, so that means it is the rate of change with respect to time. So therefore what are the things given? The given things are dr dt, considering r as the radius. So dr dt is given half centimeter per second, and also the radius is given 1 centimeter. So now I need to find out what is the rate of change of volume. So obviously volume of a sphere is 4 by 3 pi r cube. So dv dt, that is 4 pi r square into dr dt. Obviously t is a different variable, so when I am doing the derivative with respect to a different variable, I have to consider for the derivative as well. So now once I know all this, just put all the values, calculate, and after you have done all the calculation, I can see that it is coming out to be 2 pi, and so therefore the rate of change of volume of the bubble is 2 pi centimeter cube per second. Obviously it is with respect to time, so therefore 2 pi centimeter cube per second, right? Simple enough. Let us move to number 3. Number 3 is the volume of cube is increasing at the rate of 9 centimeter cube per second. How fast is the surface area increasing when the length of the edge is 10 centimeter? Fine. So now let us see what are the things given. The first thing is given is that the volume of the cube is increasing at the rate of 9 centimeter cube per second. So the rate of change of volume with respect to time is given. So that is dv dt, that is given 9 centimeter cube per second. Fine. Then as it is a cube, so what is the volume? Volume is a cube pretty much. Then what is dv dt? Let us do the derivative with respect to time on this. So now obviously dv dt is a cube derivative is 3a square but I'm doing I'm doing it with respect to t, so I have to consider dA dt as well. So dv dt is equals to 3a square into dA dt. Now let us put all the values which are given. Now obviously I forgot to write here, this is the value of a is also given, that is equals to 10 centimeter. So please, I forgot to write it. So let us put all the values and calculate. So after doing our calculation, putting all the values, I see that dA dt is coming out to be 3 by 100 centimeter per second. That is the rate of change of the edge of the cube. So I definitely require this. Why I require this? To calculate the rate of change of surface area, I need to first find what is the rate of change of the edge of the cube. So this is what the value is. And now let us move to the surface area. So what is the surface area? That is 6a square. Now remember this, nothing mentioned means I will always consider the total surface area. If mentioned otherwise, then I will definitely use that, whatever it is given. So ds dt, that is, if I do the derivative, it is 12a into dA dt. Now let us put all the values here. So 12 into 10, and dA dt I just found out to be 3 by 100. So doing all our calculation, I get the rate of change of surface area with respect to time, that is 3.6 centimeters square per second. Fine. Now let us move to problem number 4. Now problem number 4 is a big problem. We have to understand one by one. What is given? A conical vessel whose height is 4 meter and of base radius 2 meter is being filled with water at the rate of 0.75 meter cube per minute. Find the rate at which the depth of water is rising when the depth of water is 1.5 meter. So now before we understand anything, let us first draw the cone. When I am talking about a conical vessel, so let me first draw a cone. So this is the cone that I am talking about. So understand what are the things here. Let us understand the terms here. So what is capital R? Capital R, this is the radius of the cone. This is the radius of the vessel, radius of the conical vessel. Fine. Capital R is the radius of the conical vessel. Then capital H, that is the height of the conical vessel. So this capital H, this is the height of the conical vessel. This is the height of conical vessel. Fine. Then small r is representing the radius of that part of the vessel, radius of the part of the vessel where the water is, radius of the filled part, radius of the water filled part. Fine. So let us understand this. And then H is the this H is the height or depth, whatever you want to call it, height or depth of water. Fine. So these notations are very important because we are going to make use of this in our problem. So capital H, capital R represents the height and depth of the cone or the conical vessel that we are talking about, and small h and small r are the height and the radius of the rising level of water. So now two things we need to understand, that is capital R and capital H, these two are constant. Why constant? Because the vessel is not increasing or decreasing, the vessel is remaining the same. So capital R, capital H, they are not changing with time, they are constants. But what is changing with time is the small r and small h. Fine. So now let us understand what are the things given. So the things that is given, the first thing that is given is, so the height of the conical vessel is given to be 4 meter and the base radius of the conical vessel is given to be 2 meters. So these are the things given. So capital H is 4, capital R is 2. Then the water is flowing in, the water is filling up the cone at the rate of 0.75 meter cube per minute. So that means the water is actually filling up the volume of the cone. So therefore dV dt is given 0.75 meter cube per minute. And then finally it is given, I have to find the rate at which the depth of the water is rising when the depth of the water is 1.5 meters. So I didn't write here once again, but here the small h is given, that is 1.5 meter, right? So these are the things which are given and I need to work with this. So now let us come to the solution part. Now I already talked about this, that let small r and small h be the radius and height of the level of water in the vessel. So that is understood. Now this is something which we need to understand, this one. So the ratio between small r and small h is same as ratio between the capital R and capital H. This comes from similarity of triangle, which we have done in our previous classes, maybe in class 9 or class 10, I don't remember which class you have done. So just refer back to your class 9 and class 10 mathematics, you will be able to get it. How to get it? Now let us understand, this is the triangle, this is one triangle and this is the smaller triangle. So obviously if I show that these two triangles are similar, then from similarity I can write that the ratio between the sides of the smaller triangle to the bigger triangle are equal. That is the property of similarity of triangles. Fine. So now let us proceed. So from here what can I write? From here I can write this. So small r is equals to capital R by capital H into small h. Now what is the volume of the water level that is rising? The volume of water level that is rising, that is given by 1/3 pi r square h, obviously small r and small h, because that is I am talking about water. Now obviously I can't keep two variables. If I keep two variables then I won't be able to work. So let me just change one variable into another. So let me change r square, that is the small r square, into h. So if I do so, I can write capital V is equals to 1/3 pi capital R square by small capital H square into h cube. That is, I am doing what? I am replacing this value into this. Fine. Now let me do the derivative. So let me do the derivative of this with respect to time. So if I do the derivative with respect to time, so see, pi r square cap h square, this part is constant. So it is not going to be affected by the derivative, it will remain as it is. Just the derivative will be of h cube, and h cube derivative is 3h squared. So 3 and 3 gets cancelled. I am left with h square into dh dt. Fine. So now I don't have much left. What I am left with, I have to just put all the values in, do the calculation. So dv dt, that is given 0.75, put it. R is given 2, put it. Capital H is given 2, and small h is also given 1.5. So let us put all the values, calculate, and once the calculation is done, I'll see that dh dt is coming out to be 4/3 pi meters per minute, and this is exactly the answer. We are asked to find the rate at which the depth of water is rising. So this is the rate at which the depth of water is rising. Fine. Just go through the problem. This is a little bit tricky problem and also requires a little bit of understanding of geometry, something which you have left out after class 10. So you require to make use of geometry, and let me just give you a warning right here itself that this chapter may require a lot of geometry and mensuration, because you can see I am working with mensuration only at the end of the day, because I am talking about volumes, I am talking about area. So just go through those part once, remember the formulas well. Once you do so, I am pretty sure you will be able to solve the problems. Okay, so now let us move to the next problem and last problem for the day. A girl of height 1.6 meter walks at the rate of 50 meters per minute away from a lamp which is 4 meter above the ground. How fast is the girl's shadow is increasing? Now, before I go on to solve this, let me just give you something. Let me just talk about something which I missed talking about in the beginning. Now, obviously, when I'm talking about increasing or decreasing, now, obviously, when I'm talking about things increasing, then definitely, say, I'm talking about y increasing with respect to x, then that means the dy dx is always going to be positive. Now, if I'm talking about y decreasing with respect to x, in that case, dy dx is going to be negative. So always remember, if I'm working with increasing things, then I will always write the quantities positive. If I'm working with I'm decreasing things, then I'm going to write things negative. Right? So now, let us first draw the situation. If I do not draw the situation, I won't be able to understand. So it is given a girl of height 1.6 meter walks away from a lamp post which is 4 meter. So therefore, let me draw the situation. This is how the situation looks like. So what are the things represented here? So this PQ is representing the lamp. This RS is representing the girl, and obviously ST is representing the shadow, right? So given the lamp is shining, the light of the lamp falling on the girl, so obviously ST is going to be the shadow, right? So I have to consider all these things. And what is QS? QS is the distance between the girl and the lamp. So understanding this, let us start. So what are the things given? Height of the lamp post is given 4 meters. So PQ is 4. Height of the girl, that is RS, which is given 1.6 meter. Now, I have considered small a to be the distance between the lamp and the girl, and therefore it is given a girl is walking away from the lamp post at 50 meters per minute. So therefore the distance between the girl and the lamp is changing, and it is increasing actually. So increasing at the rate of 50 meters per minute. So therefore dA dt is given 50 meters per minute, right? And I have considered small b to be the length of the shadow. So now what I am supposed to find out? I am supposed to find out what is the rate of change of the length of the shadow. So actually I am supposed to find out dB dt. This is exactly what I am supposed to find out. Now let us consider some trigonometry here. Let us consider some geometry here. So in triangle RST, so in triangle RST, this small triangle, what is tan theta? Tan theta is nothing but perpendicular by base, so that is RS by ST, and RS by ST is nothing but 1.6 by B, right? If I zoom in a little bit, this is how it looks. Fine. Then in triangle PQT, that is the bigger triangle, what is tan theta? Tan theta is PQ by QT, that is 4 by A plus B, the whole thing. So now obviously the angle is same, so therefore tan theta is equal. Now this is exactly what I did in the previous problem. You see, I could have written directly that PQ, I could have written directly that PQ by QT is equals to RS by ST. Actually, this is, I could have written this directly, right? But I didn't write it, just to make you understand. So if you understand this, then you will be able to understand in the previous problem how small r by small h became equals to capital R by capital H. This is exactly how it becomes. The same logic, exactly the same logic. Okay, so now once we have understood this, so then let us move to this. So we can see why they are equal. So now let us do some calculation. So after doing all our calculation, we get 2.4b is equals to 1.6a. And then again simplifying it, I get 3b, that is equals to 2a. Now let us do the derivative. So if I do the derivative, I have 3 dB dt is equals to 2 dA dt. And I already know what dA dt is, that is 50. So let us put the value, do our calculation, and therefore I have dB dt is equals to 33 1 by 3 meters per minute. So therefore the shadow length is increasing at the rate of 33 1/3 meter per minute. Fine. So that's exactly our first class. So thank you so much. Complete the problem, and we will be having our next class, say by Friday or Saturday. Thank you.